Hello and welcome to the MOOC on optical communications. In this module we will look at the improvement that a coherent receiver provides over the simple direct detection receivers in the on-off keying systems that we considered. If you remember, in the on-off keying systems that we considered in the last module, there you saw that the receiver just consisted of a photodiode followed by an amplifier in the RF case, in RF amplifier if you want, or it would just be given to the decision circuit, right. And there we found that if you do not have any other impairments except for the noise of the receivers, which can be short noise when the bit 1 is transmitted, as well as thermal noise. However, only thermal noise when bit 0 is transmitted. In addition to that noise, the only limitation that the fiber offers is in terms of the attenuation. We found that as the length increases, the transmission distance between the transmitter and the receiver increases, then the performance as measured by the bit error rate degrades for these systems. Let us see if coherent receiver is able to bring out any kind of an improvement over the direct detection receiver. In order to do that, let us look at this picture which shows you the block diagram sense of what is happening with the coherent receiver. So, you start with a transmitter, okay, it produces a certain power. So, the transmitter is producing an optical power of P1 and 0 when you transmit a bit 0, P1 when you transmit a bit 1. This passes through the fiber is still characterized by only the fiber loss coefficient, which is alpha f, and the distance between the transmitter and receiver, which is given by the length L. At the receiver, what we are assuming at this point is that there is a local oscillator, which is a very strong optical signal coming from a local oscillator whose frequency is exactly matched to that of the transmitter. Moreover, not just the frequency is matched, but also the phase is locked to that of the transmitter. So, the frequency offset, which one might define as the difference in the frequencies between the local oscillator and the signal frequency of the transmitter laser, is assumed to be 0. So, we assume a frequency offset of 0 and we assume that phase is locked with respect to transmitter. So, which phase are we talking about? We are talking about the local oscillator phase, which is locked with respect to the transmitter phase. What do we mean by locked phase? What we mean here is that if this is how the phase of the transmitter is varying, okay, then apart from that fixed offset, the phase of the local oscillator also tracks the phase variation of the transmitter. Of course, it will never be sinusoidal like this, but this was just used to illustrate the concept that local oscillator phase is locked with respect to the transmitter phase. Okay. Under these ideal conditions, and the only limitations that you are going to get is the loss in the fiber as well as the noises that will be appearing in the receiver circuit. This part which you see I plus and I minus correspond to the output of the photodiodes, and the two photodiodes are used in the balanced coherent receiver as we described in one of the earlier modules. Okay. The coherent receiver takes in as two inputs, one is a local oscillator and the transmitted signal which is now at the receiver, and produces two photocurrents I plus and I minus. The actual or the final photocurrent that you are going to get will be the difference between the two. Because you are taking the difference between the two, any DC value over which the signal is riding from the I plus and I minus will be cancelled out. So, this one you can think of as differential output. So, this differential output will only give you the signal that is encoded in the or the signal that is riding the AC part of the signal. The DC offset values in I plus and I minus, which are very nearly equal to each other, will be cancelled out. Of course, if this was the case, then our life would have been very simple. Unfortunately, with this I, which is the photocurrent that you are looking at, you also get noise. Okay. So, both I plus and I minus, because they are the outputs of a photodiode, will be subjected to short noise, and the overall current I will be subjected to short noise plus thermal noise. Okay. What we will do is that we will examine the output of the coherent receiver and then see whether some interesting cases can be realized, which will allow us to make some concrete predictions about how the coherent receiver would perform. So, in order to do that, first we need to recall the expressions for I plus and I minus, and let us do that by remembering that the I plus is the output of the photodetector. Therefore, there is a responsivity factor R multiplied by whatever the power that is input on that. And what power is input on that? If you remember the coherent receiver that we talked about, you have two electric fields which are talking to each other. You have the signal electric field Es of t and the local oscillator signal, which is ELO of t, and the magnitude square of the sum of these two will be the optical power. So, optical power multiplied by R will give you the current I plus. If you want to find out the current I minus, this current will be equal to R, and except for a plus sign, the rest of the terms are equal, right. In fact, Es plus t by plus ELO of t and Es of t minus ELO of t are coming from the output of the splitter, and each of the splitter outputs are in turn fed into the photodetectors. Because the output power is coming through the splitter, there is a factor of by 2 here for each of them. So, you have I plus and I minus given by R by 2, this factor, R by 2, this factor. Of course, as I said, this is just the optical signal part, okay, but there is also short noise coming in because of the two photodiodes, right. So, there is a short noise plus and a short noise minus. These short noises are coming from the photodetectors that are connected to the balanced photodetector. Remember, the coherent receiver actually has two photodiodes, and each of these photodiodes will in turn look at the mean optical power, and they will generate a certain short noise, okay, and that short noise is what is that you are getting from both I plus as well as I minus. To proceed further, let us just evaluate this, the magnitude square terms. So, consider just I plus for now. I will leave the corresponding expression for I minus as an exercise to you. So, I plus is given by R by 2. Open up this one, you are going to get Es of t magnitude square plus ELO of t magnitude square. These are the two powers that, the average powers that you are going to see with the signal and the local oscillator, plus there is a 2 times real part of Es of t ELO complex conjugate of t, okay. And there is of course the short noise term that we are going to anyway have. What is this Es of t ELO conjugate of t? We have ELO of t, which is the local oscillator output, having a power of square root PL, okay, and then you have e to the power j omega LOT. We are going to assume that this local oscillator is having a constant phase, and remember that constant phase is the difference between the transmitter and the receiver phases, which we are going to assume to be constant, okay. So, as far as the receiver is concerned, local oscillator is simply a carrier signal, okay, or sorry, a local oscillator signal which is a sinusoidal carrier which has a frequency of omega LO and has an amplitude of square root PLO. Similarly, you have Es of t given as square root of Ps, which is the amplitude that you are going to get, and there is also S of t minus NTB summed over n from minus infinity to plus infinity. Clearly, this S of t is the pulse shape that we have used, and we are essentially transmitting one pulse after the other, okay. All these pulses are centered or modulated at e power j omega st, where omega s is the transmit laser frequency. So, this is Es of t, and if you look at the case when you transmit bit 1, then over one time period, let us actually look at this over one time period, for which we can remove all this summation and everything, okay. So, this in the particular time period that you are interested in, this simply becomes S of t, and S of t is the optical pulse, okay. This optical pulse will be non-zero when bit is 1, okay, and it would be equal to 0 when bit is 0. So, essentially you get a sequence of optical pulses. This would be normalized to 1, we have normalized this one to 1 without saying it so, but this is how the optical pulse shape is going to look like when you are transmitting bit 1, and when you transmit bit 0 there won't be any pulse, so that the total optical power during the interval when bit is 0 is actually equal to 0. So, going back to what is happening to I plus, you can write I plus as R by 2 Es of t magnitude square plus ELO of t magnitude square plus 2 S of t square root of Ps PLO. I am assuming that these amplitudes are going to be constants, therefore the signal power is Ps and the local oscillator power is PLO, so that essentially enters into the equation. Okay. Then there is of course in the case of e to the power j omega st, right. So, if you look at Es and ELO conjugate, you have e to the power j omega LO of t, which is getting conjugated. So, you get a minus sign here. You have e power j omega st, that would be there as it is. So, you can combine these two to write this as e power j omega s minus omega LO into t. Of course, you are taking the real part of it. So, let us basically take the real part of it. Okay. This entire thing plus whatever the short noise that you are going to get, this would be I plus. Okay. You can write down I minus in a very similar fashion. So, you have R by T, you have Es of t magnitude square plus the local oscillator signal. In place of a plus you get a minus sign here, you have S of t square root of Ps PLO, and here recognizing that omega s is equal to omega LO. Remember, we have assumed that frequency is locked to the transmitter frequency and the frequency of the local oscillator is exactly equal to the transmitter frequency. So, no frequency offset, this goes to 0. Such a scheme is in fact called as homodyne. Okay. It is a slightly older terminology. Homodyne means that the transmitter frequency is exactly equal to the local oscillator frequency. If it was not equal, then such a scheme would have been called as a heterodyne frequency scheme or heterodyne detection scheme. So, you have minus 2 S of t square root Ps PLO coming for I minus, then the exponential is equal to 0. So, the exponential of J0 is 1 and real part of 1 is just 1. So, I am going to close the bracket over here. Of course, I cannot forget the short noise that exists, and we can write this as short noise minus. The total photocurrent that you are looking at will be the difference between I plus and I minus, and you can easily see that when you take a difference like this, these terms are going to cancel with each other. This ELO of t square is going to cancel with this ELO of t square. So, what you get in turn is 2 minus of minus 2 becomes a plus 2, therefore, this becomes 4 times S of t. There is an amplitude factor out there. There is an R by 2 here, therefore, R by 2 into 2, that 2 and 2 will cancel, and eventually what you get is 2 times R. Please remember, this R is responsivity. Okay. This is responsivity which is related to quantum efficiency in this manner, eta q by h nu, as we discussed in the photo deceiver circuits. So, you have 2R S of t. I do not really have to say S of t as summation signal because I am considering only one period, and in that period, bit period, S of t can be either plus 1 or 0 depending on whether we are transmitting bit 1 or bit 0. Okay. Times square root of Ps PLO, and then you have the total noise component, which can be written as n short. N short will be defined as n short plus minus n short of minus. That is to say, this fellow is actually n short plus minus n short minus. Okay. So, this is the overall noise variance that you are going to get, and this variable, the difference between the two noises, is denoted by n short. Okay. So, this is what you have in for the photodiode. And what about the short noise variance? The overall short noise variance is going to be sigma short plus square plus sigma short minus square. If you are wondering where this kind of relation is coming from, you have to remember that n short plus and n short minus represent the short noises in the photodiodes which are used at the two branches of the coherent receiver. These are independent random variables, and these variables have both 0 mean, and they are distributed according to certain short noise distribution that we have seen, but because they are independent random variables, the total variance of these two will simply add up. Okay. What is the variance of short noise plus? This is given by 2q I plus, which is the photocurrent that you are looking at, distributed over the bandwidth of BE, where BE stands for the electrical filter that you are going to put after the photodiode circuit. So, you are actually looking at the total noise into that bandwidth of BE. Similarly, short noise minus will also be equal to 2q I minus being the photocurrent that you are going to see in the other branch of the coherent receiver. So you can write that one down, you get 2q I minus Be. You can factorize all these components out and you get I plus plus I minus. Now look at this, here you have I plus and to that you are adding I minus, right. In order to obtain the overall photocurrent you have to subtract the two, but when it gets to the noise variances I plus adds on to I minus, right. So you have an I plus adding on to this, when you add them these terms will vanish, right, because these terms are in opposite signs, so they will vanish. This one is the power that you are seeing in the received signal, this is the power in the received signal. Actually this should be rewritten as P received, okay. And we also know that this power that we are going to receive will be non-zero only when you have transmitted a bit 1. Therefore I can write this as P1R and P1R, whereas this is a constant power that you are going to get, which is PLO on both sides. So when you now add these two, there is R by 2 times P1R plus R by 2 times P1R. So this is going to be, you can write this as 2QBE, I plus is R P1R plus for the local oscillator that would be RPLO. Why did I write P1R? Because remember you might actually start the transmission at PS, but that is not what you receive. What you receive here will be depending on the length of the propagation or the length of the fiber, what you receive will be the power P1R, which is going to be, so this power is PS, which is where you start. However, the power that you receive will be this P1R, which is the actual power that you receive after a propagation length of L. So this is 2QBER, P1R plus PLO being the total short noise variance, and please remember this particular equation, okay. And this equation is also true when you have actually transmitted bit 1. What about the case when you have bit 0? So let us also designate this one as short noise corresponding to bit 1, so that we can write this as sigma 1 square, okay, and we just have the short noise. The thermal noise of course does not depend on the local oscillator power, nor it depends on the received signal, therefore the thermal noise for both bit 1 and bit 0 will be the same. So you don't really have to put them down here, okay. What about the short noise when you have the bit 0? So for bit 0 of course there is no photocurrent because your received signal P1R is going to be equal to 0. While the received signal is equal to 0, the short noise unfortunately is still going to be the same, except that P1R will be equal to 0. So the short noise here will be 2Q BER PLO, right. This is kind of the primary difference between what you are going to get for bit 0 and bit 1. The short noise for bit 1 will include P1R plus PLO, that would be the total mean optical power that you receive when you transmit bit 1, whereas when you transmit bit 0 there is no power to receive. However, the local oscillator which is sitting at the receiver is going to contribute to the total short noise, and corresponding to these short noises, or in addition to these short noises, there are also going to be thermal noises. The thermal noises are independent of the optical power, but if you are looking at the total noise sigma 0 square, this would be the short noise that we have just written down, plus there is a thermal noise, right. So you can write the thermal noise here, and then you have a thermal noise spectral density of 4 kT by RL multiplied by the total bandwidth that you are looking at, which is equal to BE. So this would be the thermal noise, which is also the same as the thermal noise for bit 1. So we have looked at the total short noise and the total noises here, and you can actually, this is all that is required for you to go ahead and calculate the bit error rate, by calculating the Q factor and then applying the relationship between the Q factor and the bit error rate. That is what you can do. However, it would be very interesting to see what actually turns out in practice. In practice, what we do is we want to operate the signals at what is called as the short noise limit. Why do we want to do that? Suppose we operated them not at the short noise limit but at thermal noise, then bit 0, because there is no optical power input to it in terms of P1R, the variance of that will be slightly lower compared to the variance of bit 1, and this, by how much this difference would vary, because sigma 1 short noise square plus thermal noise that is there, sigma 0 short noise square plus thermal noise. So, thermal noise contributions are equal for both, okay, and you do not really want to operate with the thermal noise limit because that limits the speed of operation. So, you want to operate in the short noise limit. But while you are operating in the short noise limit, sigma 1 is slightly larger than sigma 0 because there is P1R sitting in sigma 1, right. So, you can see that sigma 1 short noise square is given by P1R plus PLO. Because of this P1R plus PLO, this would always be greater than sigma 0 short noise square. However, this of course sets you a problem with putting the limits. So, in one instance you have a Gaussian random variable, that is what we have assumed. This is say sigma 0 square. This is going to be fixed, it is not going to change, right, with the fiber length, because this is all determined mainly by the or purely by the local oscillator power. However, the power corresponding to or the short noise variance corresponding to sigma 1 will change depending on the variance of that depends on the received power, okay. When the length of the fiber is very large, then P1R will be very small. So, you can kind of say that it would have the same short noise variance as the 0 bit short noise variance. However, at lower powers it is not really so, right. So, you actually have a variance which is changing with respect to, so you actually have a variance which is changing depending on the length of propagation, right. So, this variance of sigma 1 square depends on the length of propagation simply because P1R depends on the length of propagation. So, setting the threshold will now be very difficult. You can't have a simple coherent receiver circuit and say, okay, this is the coherent receiver circuit, go ahead and use it, because then someone also has to tell you what is the length and you have to do a manual adjustment of the thresholding that separates bit 0 and bit 1. In order to avoid this problem, what we normally do is we have a PLO, the local oscillator, completely dominating the received power. Even under the worst case scenarios, you have PLO which is much larger than P1R. The advantage of that in terms of the signal is that you have PLO which is much larger than the received signal P1R. Of course, P1R will be equal to PS when you transmit bit 1. So, you are essentially getting some sort of a gain without actually using an optical amplifier. You are getting some sort of a gain because you are using this PLO. Okay. So, the total photocurrent increases, of course the noise also increases, but consider what is happening. When PLO is much larger than P1R, the variance for 0 bit is exactly or very close to the variance of bit 1, and because these bits are the same, you can simply set the threshold right at the halfway point. For example, if my P1R is equal to 0 dBm, which is 1 milliwatt, and P0 is equal to 0, you can set the threshold right at half milliwatt voltage or half milliwatt current depending on what you are looking at. So, this sort of a equalization of the variances is very important, and in order to achieve that you want to operate this in under the condition that PLO is much larger than P1R. When you do that, sigma 1 is approximately equal to sigma 0. Of course, the short noises are approximately equal to each other. The thermal noise was anyway equal to each other, but we are also assuming that PLO is such that we are operating under the short noise limit. So, we can limit or we can neglect the thermal noise. Okay. So, sigma 1 will be approximately equal to sigma 0, which is approximately equal to sigma 0 is given by square root of 2q BER PLO. Now, if you recall the Q factor that we described for the on-off keying systems with the coherent receiver. So, I am going to write this as coherent receiver on-off keying thing. This we had defined it as I1 minus I0 being the photocurrent when you transmit bit 0 divided by sigma 1 plus sigma 0. Here sigma 1 is equal to sigma 0 and I0 is still equal to 0. What about I1? I1 is given by 2 times responsivity, and S of t is just equal to 1 when you transmit bit 1, and PS becomes P1R. So, substituting these values, what you get here is 2 times R square root of P1R PLO divided by sigma 1 plus sigma 0 is nothing but 2 times sigma of either of the two, right. So, it would be square root of 2q BER PLO. 2 cancels on both sides. You can clearly see that there is a PLO square root here in the denominator, which can be cancelled with a PLO in the numerator. although PLO was used to establish the short noise, it finally turns out that in the Q factor PLO does not make an entrance. Okay, so your results are independent of PLO as long as PLO is much larger than the received signal, so that both the photodiodes and the entire coherent receiver is operating in the short noise limit. Okay. Further simplification of these equations can be made, and you can show that because there is a square root r here, there will be a square root r in the numerator, there is a P1 r here, and you can show that this is going to be r P1 r divided by 2q BE. Okay. Now the energy P1 r can be rewritten as the power P1 r times TB. Of course, energy being power into time, that is where, so I had confused it a little bit earlier. So you can write down the energy as the number of photons that you are going to receive times h nu. So this allows you to write P1 r as number of photons that you received times h nu divided by TB. You can substitute that equation into this one, also substitute r is equal to eta q by h nu and simplify the relationships. What you get for the on off keying coherent receiver is an expression which is very interesting. You get eta P1 r divided by 2 h nu times BE. Okay. Of course, you can substitute again, as I said, for P1 r, which would be equal to square root of eta, and P1 r is nothing but the number of photons that you receive divided by h nu divided by TB 2 h nu into BE. H nu cancels on both sides. Now you get square root of eta NPH divided by 2 BE into TB. If you are using Nyquist pulse shaping, then to transmit signals at a rate of B bits per second, okay, you need a bandwidth of about B by 2 or 1 by 2 TB. Assuming Nyquist pulse shaping, this is what the bandwidth that you require. So you can substitute BE as 1 by 2 TB in this expression and see that the denominator simply cancels out, right, or becomes equal to 1. So the on off keying for the coherent receiver is given by square root of eta times the number of photons that you are receiving when you have transmitted a bit 1. So let me just modify the notation and then say this is NPH1R, where NPH is the number of photons that you have received with 1R, and this is what you are going to get, and you can recognize that the number of photons that you receive when you transmit a bit 1 will be 2 times the average number of photons that you are going to receive. Okay, 2 times the average number of photons, and therefore the Q factor for the coherent receiver is given by square root of 2 eta the average number of photons that you receive. Okay, and this is the Q factor. If you quickly evaluate this, okay, you will see that the BER of course increases, but there is a 3 dB improvement with the direct detection receiver and the coherent receiver, which is operating under the short noise limit, okay, as the fiber length increases. You will also see that the approximately the length with the coherent receiver will be twice of length with the direct detection receiver, and all this is happening because you are using this extra degree of this one because of the coherent receiver. Okay, we will stop at this point and consider the limitations due to dispersion in the next module. Thank you very much.